Hey, I think we can get started. Hello, everyone. Welcome to the Healthcare AI Forum. My name is Yuan Luo, and I'm the host of the forum. Today, for our last session of this academic year, we are grateful to have our friends and colleagues from Ohio State to present to us some of the leading state-of-the-art developments in terms of large language models and agents. And leading the group will be Dr. Xia Ning. And Dr. Ning is a professor in the Biomedical Informatics Department and Computer Science and Engineering Department in the College of Pharmacy at Ohio State. She's the Division Chief of AI in Digital Health at BMI and the Associate Director of Biomedical Informatics at Ohio State's CTSI. Dr. Ning's research is on AI and machine learning with applications in drug discovery, healthcare, and e-commerce. And Dr. Ning is a fellow of AMIA and a senior member of the National Academy of Inventors. Now I would like Dr. Ning to introduce her students and their presentations.
Thank you, Dr. Yuan, and thank you, everyone, for giving us this opportunity to present our most recent work, particularly on large language models and agents. So today we have three students from my lab, Reza, Vishal, and Frazier, and each of them will present our recent work on large language models and agents with applications in two very different domains. One is on the clinical side, about clinical notes analysis using large language models, and also large language model-based agent for drug discovery and large language models for for molecule optimization. So let's start with Frazier. So the first presentation is from Frazier on LIDDiA, a language-based intelligence drug discovery agent. So Frazier is a computer science and engineering PhD student at OSU. His current research focuses on intelligent agents for navigating preclinical drug discovery tasks, such as retrosynthesis and target-based drug design. So Frazier worked as a research scientist at Georgia Tech Research Institute before he joined OSU. He received his Master's of Science and Bachelor's of Science in Computer Science from the University of Cincinnati. So Frazier, it's all yours.
Thank you, Dr. Ning. All right, okay. So thank you, Dr. Ning, and thank you everyone here for having me today. As Dr. Ning mentioned, I'll be sharing some very recent work that we've done on a language-based intelligent drug discovery agent called LIDDiA. So just an overview, I'm going to go through an introduction, give some background. I'll talk about the method, go through our experiments, key results, give some conclusions, and then, acknowledgements and references, and I'll have time to take questions. So drug discovery, in case anyone in the audience isn't aware, it can take years and cost billions of dollars. It's not a simple process. It has a lot of setbacks. It can really take a lot of different turns going from the initial need for a drug to an actual molecule that can be clinically tested. And recently, we've had a lot of in silico tools, a lot of computational tools to try to accelerate this. So a lot of generative AI tools for generating molecules that fit binding pockets, for simulating how well those fit. To improve these various properties, and the list goes on. The thing is, each of these only addresses a very small part of the overall drug discovery process, and you still have medicinal chemists and computational chemists who are trying to work on orchestrating this overall pipeline and making this discovery. And we want to see if we can maybe do something, do something to automate that a little bit more. In parallel with all of these advances, we also have large language models, which I'm sure you're all familiar with: ChatGPT, Claude, things like that. These large language models not only are good at crafting language, but they're also powerful reasoning engines using the reasoning inherent in natural language generation. And they've actually shown promise in the intelligent use of tools. So they can actually interact with some environment by saying, I want to use this tool with this input and observe some results and make a decision based on that. So these LLM agents there's been a lot of recent work on this. And we're wondering, could we use LLM agents to automate these? This is exactly where LIDDiA comes in. So from a user prompt saying, I have a target pocket that I want to make a drug for. Can you give me at least 5 molecules with these properties? And make sure that these aren't just a bunch of very similar molecules, but make them diverse. Make sure they're not the same as existing drugs. Can you do that, LIDDiA? And LIDDiA, through the use of tools, generates a set of diverse and novel molecules that are high quality and could go on to become potential drug candidates. And so to look at how LIDDiA does this, to get some idea of what we're doing here, LIDDiA has 4 main components. The memory holds that user prompt, all of the information really that LIDDiA has been processing. So initially it's just the user prompt, but as we go on, it will store all of the candidate molecules that have been generated, their properties, their binding affinities. It'll also store the action history so LIDDiA can see what she's tried and what maybe worked and didn't work. Next is the reasoner. This is LIDDiA's brain, where she chooses to take certain actions, use certain tools to generate or modify more molecules to answer this prompt, this need. Those to start with LIDDiA. But this is extendable. So right now we're looking at generating molecules based on the structure, not searching some list of existing molecules, but rather generating them to fit the protein from the beginning. This is different from virtual screening that you may have heard of, where they do have a library of molecules, a list of molecules that they search. After that, we may need to optimize these molecules. They may be good on some properties, but not all of them. So we're using some basic genetic algorithm methods for improving those properties. And then, of course, we need to search. We need to narrow the molecules down to a set that is diverse and novel and good on all of the properties. And after it does each of these things, the result is a set of molecules that gets evaluated. And here we use more tools. So the evaluator will run the docking simulation, property prediction, evaluate the novelty and the diversity, and then send that information back to the memory. If the evaluator finds that all of the properties have been satisfied, it will actually return that to the user and stop early. So as we test this, we want to see, well, how well does it work, right? To start, we took 30 target proteins from different disease categories. These are proteins we could find a ligand binding pocket for, so we knew there was already an active site there, and we extracted these pockets. We wanted a diverse set of proteins because we weren't wanting LIDDiA to just be a single focused agent. We wanted it to be generalizable to many different targets, many different needs. We actually looked at Chembl to find existing drugs, and we used that to sort of benchmark the goal for LIDDiA. We took the average of all of those different property scores that you saw previously, and we said we want to make sure we're at least as good as the average existing drug for this target. For novelty, we looked at structural dissimilarity, basically. So we're wanting to make sure that these are very novel and also very diverse. So they're not the same as each other, and they're not the same as existing drugs. And that brings us to our overall performance. So I'm going to take you, I know this is a big table. I'm going to take you through it step by step. The very first box I'm going to highlight, again, we're comparing LIDDiA against what here? We're comparing it against molecule generation methods that just generate molecules. They don't optimize, they don't screen. The thing is, there's nothing exactly like LIDDiA out there that can do this iterative process. So we were trying to find baselines that were the closest that we could find to this. In addition, we thought, well, you could just ask GPT, give me some drugs. You could ask Claude, you could ask GPT-01, all of these things, and maybe it can give you some good molecules. And so we tried all of these. And in the first point, we're just looking at how many drugs did we get, or not drugs, how many molecules did we get from each of these methods? And were they valid, right? Were the representations something that we could actually interpret as a molecule that didn't violate any valency rules or things, something that could be maybe possible. And in general, most of the methods did well with this. So there's not the thing to note with the LLMs especially is that they can generate some invalid molecules on occasion. The second box here is where we start looking at, okay, what's the quality of these molecules that were generated? So looking at all of the molecules returned by each method, we actually see that these other methods, they're good on some properties, but not all. So we're looking at a quantitative estimation of drug likeness, which gives a general sense of how similar the solubility and other various properties are to other drugs. We're looking at Lipinski's rule, which is a common rule in drug discovery. Synthesizability through synthetic accessibility score. VNA is your docking score, so it's a binding affinity. And then novelty is also listed there, so comparing it to existing drugs. Again, some of these methods are good on some things, but not all, whereas LIDDiA is able to consistently generate molecules that are good on all of these properties. Not just generate, but optimize and filter and return those. And then finally, we're going to look at diversity, right, which is looking at the set of molecules together. So again, if you look at the molecule generation methods that use diffusion, so pocket to mole and diff-S-mol, if you look at those, they're able to generate diverse molecules, which is great. But when you start looking at whether or not those molecules are high quality, given all of those properties I mentioned in the last box, it's not as great. And in the other methods, again, you see they're really lagging behind here, whereas LIDDiA, again, is able to consistently deliver on all of those by considering all of them. So our total success rate at the end across those 30 is 73.3%, which is pretty impressive. How does LIDDiA do this, right? What's the idea here? Again, it's using 3 simple actions: generate, optimize, and screen. It can, of course, specify more arguments to each of those. But these actions, it's not just using it in one straightforward approach for every single target. It's adapting it to each target, right? So here we can see for CDK5, it starts with generate, and it always actually starts with generate, so it has some molecules to work with. But then it optimizes and then it screens. And then when it finds that screen didn't give it the set of molecules it wants, it optimizes again. And it does this, it continues to do this until it finds a set that succeeds. But if we look at DRD2, it doesn't do the same thing, right? It optimizes twice and then screens and then it's done. Here it's both optimizing and screening to try and find a set that works. Even in the failure cases, it's not consistently making the same mistake, right? So here you see that these are not, in some cases it optimizes 3 times, twice. It's screening in different patterns. So the key point to note here is that LIDDiA is doing something based on the results it's getting. It's not a simple loop. It's using its reasoning capabilities to really orchestrate this process. And we do have a case study on EGFR. EGFR is an important gene for a number of things, but especially for cancer. It's an epidermal growth factor protein. You guys, many of you have probably heard of it. For this, LIDDiA is actually, we asked it to generate at least 5 molecules. It gave us 12 that met all of our criteria. For each of these, we're comparing it to a few selected drugs that already are known to target EGFR. Specifically, we selected the one with the best binding affinity, the one with the best QED score, and the one with the best synthetic accessibility. We also compared it against the ligand that came from the PDB entry that we extracted the pocket from, just for good measure. And here, what you see on the right is every red box is where the LIDDiA generated molecule, indicated by a number, does better than the drug listed on the left on that particular score, that particular metric. Something to note here, of course, you see like almutinib, which is the best performing one, the best performing known drug for EGFR on binding affinity. We're still generating molecules that bind better than almutinib. And it's not just that. Those same four molecules are also synthetically accessible, more synthetically accessible and also more drug-like by the QED estimation. So again, these are some very interesting results showing that we're competitive with existing drugs in what we can generate. So in conclusion, LIDDiA is an intelligent agent for automating target-driven in silico drug discovery. It's the first of its kind. We can easily extend it, and the results are demonstrating that it can navigate this landscape despite the complexities and balance many requirements. Acknowledgements, my co-authors, funding, and of course the fellow Ning lab members. And I know you're going to hear more work here in a moment, but I included a QR code in case you're interested in our other things. Thank you.
Thank you, Reza. So I believe there are several questions in the from the audience. Would you like to take the questions? So
yeah,
I think the first question is so which method, if any, are you using to amplify the reasoning of the large language models?
Yeah, so we are using prompt engineering. I don't know why it's trying to access the camera, but we're using prompt engineering to tell the LLM what we want, but we aren't doing any sort of fine tuning or anything of that nature. I suppose another thing that we're doing to sort of amplify the reasoning is that memory component that I showed, right? We retain all of the information that's been considered throughout the process, and that memory component generates a summary each time. So the LLM itself gets a very nice, clean, summarized version rather than just a bunch of molecules. Those things are cool.
Yeah, and another question here is, do you start by giving LIDDiA structures or properties of existing compounds so as to reduce the dimensionality or search space of its potential results?
So we don't give it the structures of existing compounds. Here with chemical drugs, we give it the ability to compare for novelty purposes to the existing drugs. But aside from that, I mean, really, it's just the sort of that baseline scoring that I described. It's not using these drugs in like a ligand-based drug design way. That's not to say that we couldn't extend it to do that in the future, though.
Yeah, so all the molecules are generated out of LIDDiA. It's not like LIDDiA is search the existing chemical space. It's all the components here, particularly generate tool here, uses all the generative AI method to generate new molecules, right?
Yes, yes.
Okay. So probably another example here, any average size molecules generated. So how large the molecules are.
So we have some examples. I don't know the molecular weight off of the top of my head, but we do have some examples in our paper showing the molecules. They are all small molecule drugs, though. We aren't generating like you know, we aren't generating like polymers or anything like that. No antibody design here. It can really vary too, depending on the size of the pocket. Yeah.
Right, but in overall, those are small molecules and very drug-like.
Yeah, you can see actually these examples here in this figure are generated from ours. So
yeah. So I think there is one question is what percentage of molecules that LIDDiA generate do not exist in no database?
So I would say most of them. I mean, again, the novelty here, we're comparing, even if it's similar structurally to existing drugs, because we're using this structure-based drug design tools within LIDDiA, these are not these. I don't have an exact number for you, but generally you don't find these in existing databases. So these are all generated based on the pocket.
Okay, I will answer them online. Okay, I think that's probably for the first presentation. Thank you, Frazier, and thank you for the audience for all the questions.
Thank you.
Then let's move on to the second one. Just a quick reminder, each of the students has 20 minutes, including all the Q&A. So the second presentation is from Reza on how to use large language models to deal with the clinical nodes. So Reza is a first-year PhD student in the computer science and engineering department at OSU. He has been working in my lab for about 1.5 years with experience in large language models and for clinical domain and drug discovery. He received his master's degree in computer science at OSU and his bachelor's degree in communication engineering in Indonesia. So Reza, go ahead.
Thank you for the introduction. So I'll just pull out the presentation and display. So hopefully everyone can see my screen. So this is a work that I did with my professor in a lab last year. It has been recently accepted to the NACL conference, and just 2 weeks ago, I presented this paper in the conference. Yes, so essentially this is a paper about information extraction on clinical narratives. And so I'm just going to give a brief background for people who are not familiar with clinical narratives. So essentially, clinical narrative, it has a lot of information about a patient, and essentially a lot of these information, they are only exclusively available in clinical narratives. So that's why extracting the information from them is a very interesting problem and very useful for clinicians. But the problem is that extracting this information is actually extremely difficult. The problem lies in the language, because the language that used by the clinicians they have their own language essentially. It's more like a domain specific language, and also the format, the grammar that exists in clinical narratives, they are different than what we usually see in in our daily lives. For instance, so the exact problem that I want to focus on, at least in this paper, is more on the name entity recognition. So essentially, clinical name entity recognition, it aims to recognize the key entities that exist in the clinical narratives. And you can see some examples in the slide of what it means by the key entities in the narrative. And it is also one of the key challenges in information extraction, because these entities are essentially useful for clinicians. So I also want to talk about some of the prior methods that exist for clinical name entity recognition, and there have been several methods. And if I were to categorize this method, the first one, I would categorize it as traditional natural language processing method. It is effective, meaning that it works, but the problem that it is fragile, meaning it's really difficult to make rules for all of the cases that exist in extracting information from clinical narrative. The second approach, which is more popular in recent years, or several years ago at least, it's using supervised learning. It shows that it has a high performance, meaning it works, but the problem is that for supervised learning, it requires significant annotation, and it's really difficult to annotate clinical narratives, because not just anyone can annotate clinical narratives. Like we need domain experts to annotate these, and it's also not scalable, because the amount of abilities that domain experts are interested, there's a lot of them, so it's not really scalable to extract a lot of them. And so essentially what are the alternatives that we can use to tackle this challenge. So I think all of you know where this goes. Essentially, there have been a lot of progress in large language models, and there have also been a lot of general large language models that have been developed. And I'm pretty sure everyone is familiar with ChatGPT or Claude or Mistral, for example. And in parallel of this development, people also start developing what is known as a task-specific large language models, especially for name entity recognition. And well, they're also known as the open NER LLMs. So some of the examples include universal NER and GNER models. So the next part is that I want to analyze how does these open large language models, open NER large language models perform in clinical NER tasks. And I found that using these large language models to extract these entities like medication, treatments, medical problems, medical tests, I observed like there's a significant gap in extracting the entities. So when it comes to extracting medication, for example, these large language models, they perform really well with a performance about 85% F1. But when it comes to extracting treatments or problems, the performance is actually below 60%. And that's actually pretty low. So what is happening? And if we were to think about it, let's say that, for example, treatment, there's a lot of things that can be considered treatment. And one of them is actually medication. So the idea is that what if, let's say that if I want to extract treatment entities, what if I use medication as the input to extract these treatment entities? And I found that by using this simple idea that I have, I can actually increase the performance of extracting treatment entities to about like 70%, for example, just by specifying I want to get medication to get these treatment entities. And yeah, essentially what we found is that we can capture most treatment entities just by specifying medication instead. And from this observation, I propose a framework that we can use to extract clinical narratives using open NER large language model. And I call this framework entity decomposition with filtering. And I'm going to talk about this method a little bit in the next few slides. So the first example is that let's say that we want to extract treatments from a discharge summary, for example. So the first component of the framework, the entity decomposer, means that instead of saying I want to extract treatments, how about we decompose these entities? So what can be considered as treatments? So for example, in this case, treatments can be medications, it can be medical devices, medical procedures, and so on. And after we get these entities, the next step is to, So when it comes to implementation, there are several ways we can implement this entity decomposer. We can use a medical knowledge bank, like a unified medical language system. We can also ask clinical experts. So what are treatments, for example? And the easiest way is that we can also ask ChatGPT, what are entities that falls under treatments, for example. And so the next step is that after we get these entities, we will use the large language models to extract each of these entities. So for example, for medication, we have aspirin and antihistamines. For medical device, we have NG feeding tube and so on. So for each of these entity subtype, that's what I call in the paper, we will call the subtype entities for each of these. And once we have that, we also have, for implementation, we are using LLM train specifically for NER for this component. And for the next step is the filtering process. So essentially for each of these subtype entities, we want to know whether these entities are actually treatments. Because we found that, for example, some of the subtype entities like abdominal CT scan, it's not really a treatment. It's more about a medical test. So we want to remove those kind of entities using this component. And how do we implement this component? At least in the paper, the most simple method is just to use a large language model. And at least from our experiments, we found that any large language models that understand basic clinical terminologies will work for this component. So after the method, I'm going to talk a little bit about the experiment results. So we have this table. So we did experiments on some of the open NER large language models available. We experiment on several data sets which have their own entity types, and we also compare with supervised learning. So the first observation that we found from the experiment is that this framework actually improved across models, across metrics, F1 recall precision, across data sets, and also across entity types. And we can see like the improvement is not trivial. It has about something like plus 5% to plus 10%, for example. And on average, the framework improves by about 2.5% and 5.8% on these two models, uni-NER and also GNR models. Another observation that we found is that when we compare the performance to supervised learning, for example, our framework is actually more robust to entities that is outside the training data from the supervised learning method. And you can see like the performance difference is about 10% for this specific entity that is not inside the training data. So why does our method works? So essentially, one of the components that we have inside the framework, the entity decomposition, it can capture most of the previously missed entities. And we can see that when we compare the entities that are not captured, comparing between without using entity decomposition, the purple one, and compared with the orange one, we observe improvement on all of these entity types across all of these data sets. And just to show you a specific example, for example, for treatment and medical problem entities on this specific data set, the improvement is about 15 to 20% improvement. We also want to emphasize that the framework that you have is not limited to just large language model. The framework can also be applied to other language-based models like BERT models, for example. So we use this specific model, the GeLLMO model, which is a recent work for entity recognition, and we test the model on the same data sets, the same entity types, and so on. And we can say like when using this model, we also observe similar improvement. And if we were to calculate the average improvement, on average, this framework improves about 7% on using this model. So these are the conclusions that we found from this work. So first is that we present a simple framework called the entity decomposition with filtering, or EDF, that can improve existing open NER large language models on these name entity recognition tasks. And the main key idea that we have and why this method works is that the key idea is that we decompose the entity recognition into several retrievals of entity subtypes. And using this idea, we found that this framework can achieve improvement across models, entities, metrics, and data sets. It is also robust to supervised method, and also it is flexible enough that it can be applied to non-prompt language-based models. And these are some of ideas that we have for future works, like how does this framework apply to other domains, what are the applications, how to further improve the framework performance, and also analyze the performance using proprietary models like ChatGPT and Claude, for example. And this is the acknowledgement. and also some of the reference that we use in the presentation. And thank you for listening, and I'm happy to take any questions.
Thank you, Reza. Let's see if there are any questions from the audience. It's fine. So in case anyone has any questions, please feel free to reach out to Reza. So probably let's move forward to the third presentation. Thank you again, Reza. So the third one is from Vishal on how to use large language models for specific tasks in drug discovery. So Vishal is a final year PhD candidate in the computer science department at OSU. His PhD research focuses on large language models and representation learning. He is broadly interested in large language model reasoning and agentic workflows for scientific tasks. He received his master's in computer science from OSU and a bachelor's in computer science from Indian Institute of Engineering, Science, and Technology. So, Vishal, go ahead.
Yeah, thank you for the introduction, Shia. Thank you, Yuan and others for having me. I'm going to present this recent work on molecular optimization using large language models. So as my colleague Frazier already gave an overview of the drug discovery pipeline, that the entire process takes about like billions of dollars and over a decade to fully develop a drug from end to end. Essentially, it's starting with target identification in the first panel to the approval by the FDA. So it takes a lot of years and a lot of money to finally get a drug to the market. And as you can see in this figure, there are several stages in this entire pipeline. Actually, in our lab, we have different methods to tackle each of these stages. However, for this presentation, I'm going to focus on our method, which focus on lead optimization. So to people who are not familiar with the term lead optimization is essentially when we have some molecules which are already drug-like, which are known to bind to certain protein pockets. Maybe for a particular disease, we are trying to develop a drug, and that we have developed some molecular structures that bind to protein targets. But there are certain properties which are not good enough, and we need to improve those properties like solubility or toxicity and things like that. So the lead optimization process essentially takes a molecule which we call a hit molecule, which binds to certain protein targets, and then we try to optimize or improve some properties to make it even better. But there is a key requirement here, which I will talk about later, is about maintaining the core scaffold or the part of this structure which is actually responsible for binding. And this is very crucial because we don't want to change the molecule too much that it changes its binding affinity to the protein pockets. And this process itself is very important. It's one of the most important stages, as you can see here, because if this process is not good enough, then it will fail the later stages and essentially costing a lot of money and time. So there are several challenges in lead optimization. So as I mentioned, there can be different kinds of properties we want to improve. And these properties could be correlated, or it could be uncorrelated, or it could be actually diverse enough, because as you can see, it could be some admit properties, it could be some context-specific properties like inhibit to improve blood-brain barrier permeability. So to people who are not familiar with these properties, we sometimes when we want to develop drugs, for example, antipsychotic drugs, we want to improve those targets, the drug targets that reside in the brain. So the drug has to permeate the blood-brain barrier. So it's like a membrane. So we have to develop drugs that can improve that has better permeability so that can reach the protein target that resides in the central nervous system. However, sometimes you may also want to reduce those properties because you don't want to cause side effects when the target is not in the central nervous system. And we have these multiple properties which can often be conflicting and competing. So the process itself is very difficult to model because we have different properties and diverse properties which can be competing and conflicting. So the process, like traditional method, can be iterative. So you can optimize one property, you find that it's not good enough, and you go again and optimize it. So it is a very lengthy process. So what about computational approaches, right? So we can develop methods, and there are methods that can optimize molecules. However, we found that most of these existing methods optimize or involve only optimizing one or two properties at best. So but if we look into like practical optimization setting, we are often optimizing multiple properties, at least 3 or 4. And so we need to develop methods that can handle multiple objectives. And actually, there are some methods which can do it, for example, reinforcement learning-based methods, but that would require designing reward functions to model those multiple objectives, those multiple trade-offs, and which is itself non-trivial. And there are some evolutionary algorithms like genetic algorithms. If you're familiar with that concept, it starts with a population of an initial population of molecule and iteratively optimize it. And the problem with this method is that it often creates entirely new molecules. And that means that that new molecule will not have the core scaffold that was responsible for binding in the first place. So it defeats the purpose of late optimization, and actually that becomes a generation problem and not an optimization problem. So and overall, all these methods, we find that they are not generalizable, meaning you train a model to optimize, let's say, BUBP, blood-brain barrier permeability, and optimize QED separately. So you have a model that can optimize each of them separately, but cannot jointly optimize both of them. And this is a problem because in practice, we'll often want to optimize all of them, not only two, maybe multiple together, right? So we thought, what about LLMs? Can they do better? And there are some preliminary work that can that uses LLMs to develop optimization models. But again, we found that there is no notion of a unified model or one single model that can handle multiple tasks. What they did is essentially they tried to train separate LLMs for each task, and that is not scalable at all and very expensive, because if you have separate models for separate tasks, and there are thousands of combinations that that could be useful in real life, so you will have thousands of models, and that's not scalable at all. So what we want to do is we want to have a foundational model. As all of you are probably familiar with GPT-4, and you have seen there its good capabilities to handle like novel tasks at this time. So that's our motivation. So we have several contributions to address these gaps. So first, what we wanted to do is we want to have use instruction tuning, and I will explain the concept of instruction tuning. But essentially, first, to train the large language models, we need to create a data set to train them. And as of this moment, when we started working, there was no such data set. So we started first by building the data set that has multiple tasks involving multiple properties. In this work, we have 6. So we have 6 properties jointly optimized at a certain in certain tasks. Once we created those data set, then we show a framework of how to tune those large language models in a parameter efficient way, which is not very expensive, in the sense that we are not really tuning a lot of parameters. And actually, the model seems to learn only from thousands of examples over time. And we also have now a framework to train one unified foundational model that can handle multiple tasks using, when we train the model, we essentially train it all possible combinations of properties we have. And that would give us a foundational model, one single model that can handle different tasks during test time. I will briefly go over the data set without going to a lot of details, but this figure and this table shows, this table actually shows you the difference between our method and the only other previous work that actually have task-specific model only, and they're only focused on 8 tasks, which involves up to 2 properties, and we have 6 properties in our project. So I will briefly go over over the task construction. So what we do here, essentially, we create this different property combinations of all possible 6 properties. And for each such combination, like task with 1 property, 2 property, 3 property, and so on, we find pairs that has improvement in all of these properties. For example, for the 3 property combination, we have, for example, BVP, DRD2 inhibition, and lipophilicity, and we want to improve all of them. So we find pairs which are structurally similar enough, but has a noticeable improvement in all of these properties. And the idea is that when we have such pairs, for example, in this task, we want to optimize mutant toxicity, lipophilicity, and QED. These properties are kind of key admit properties. So the idea here is that you explain what you want in natural language. So you don't need to define this reward functions or like which are very difficult to actually optimize and define when you have multiple competing properties. So we can just explain them in natural language that what I want. And in the instruction, I also mentioned what exactly what the LLM should do. For example, it should keep the structural changes minimal so that it does not lose the core scaffold. And the idea here is that instruction tuning, meaning that we provide this to LLM, and the LLM actually minimizes, tries to predict the next word. And intuitively, what it does, essentially, it tries to follow what is the input here and what is the output here. And by following this kind of instruction, the LLM will eventually learn from multiple examples that how the molecular structure changes to improve certain properties. That is the key idea here of instruction tuning. So and then once you tune this foundational model, we have different tasks for in distribution, out of distribution tasks. So once we tune this model on different instructions that covers different property combinations, essentially, you can have one single model that can handle all of these different tasks. And then we wanted to evaluate that how this model would perform on tasks that covers like scene property combinations. For example, if I look at BVP, DRD2, PLOCP, if I use this combination in training, and if I want to test that how this model would perform this kind of optimization, which is already covered in training, we consider that to be an in-distribution task. And if we have a task combination, for example, mutagenicity, PLOCP, QED, this property combination was actually not covered in training, meaning that, for example, the model was trained to optimize mutagenicity or PLOCP or QED separately, but it was not optimized, or it was not tuned to optimize all of them together. And this is a very meaningful setting, because if we think about it in practice, it may happen that when we deploy this model, we find a new trade-off or a new combination that we didn't think about before, right? So we want the model to perform well on such tasks as well. I will briefly go over the results. I know it's a bit dense here, but the key takeaways from here are that we compare our models, which are the first time looking at the task-specific models, meaning we tune the model specifically on each of these combinations separately. So these are all separate models. This is just to show a baseline, like how instruction tuning works. So it seems that instruction tuning works really well because these models can outperform the general purpose off-the-shelf large language models like Cloud, even Cloud with 5-shot. And we also found that the generalist model can outperform all other baselines on in-distribution tests. And more interestingly, we find that on out-of-distribution tests, on unseen tests, our model can outperform the strong general purpose model like Cloud with 5 shots by a significant margin, with which, I mean, if you look at the success rate, which is the percentage of molecules that were optimized, it seems that our model can do it's better over Cloud by as much as 150% in terms of success rate. And also our optimized molecules have larger improvement on each of this property. And this is evident on our case studies. If we look into each of this case study here, which is optimizing the left side molecules to the molecules on the right side. On the first row, we have our model, and the second row, we have the baseline. And it seems our model can do a much larger improvement. And also it can retain the core scaffold, as you can see in the figure. But in the baseline, it's changing the core scaffold, and it's not making good improvements. Right. So our model seems to be very promising. And the key takeaways here essentially is that we are the first to show that instruction tuning works and actually can outperform the closed source LLMs. And we also, for the first time, come up with this generalist model training framework. And we have this one foundational model that can tackle multiple tasks. You are more than welcome to look at the paper. This is the paper link and has all the link to the data sets and the code. With this, I will yield for more questions. Thank you.
Thank you, Vishal. Let's see if we have questions from the audience.
Actually, I have a question, so if I could jump in first. So your MUMO instructor dataset is deliberately built by prioritizing tasks that require more than 3 properties improvement, and with careful attention to similarity constraints, such as you require that the tiny model score is greater than 0.6, and also you consider realistic trade-offs, such as balancing the blood-brain barrier permeability, toxicity, and intestinal absorption. Can you elaborate on the curation pipeline, and especially how you selected those properties and their combinations and the thresholds to avoid bias towards easy optimizations?
Yeah, this is a great question. So when we started these pairs, we took this from one of our previous work, actually. These pairs are different in only one disconnection site at one fragment, meaning the difference in each of this molecule pair is only one fragment replacement. And so by default, they're already very similar. And we also checked that the similarity is at least 0.6. And then we come up with the 6 properties. We can add more. Actually, our framework is extensible to more properties, right? You can add more. But for each of those properties in literature, we already have standard like thresholds to determine what is significant improvement. And then I also found that each of those delta differences between each property across each pair, that actually the threshold was chosen to be, I believe, 60 percentile or something across all the pairs. So to make sure that those differences are significant enough and not like minor differences. Yeah, does that answer the question?
Yes. And great, that's great. Thank you, Vishal.
Yeah.
So I see that we are only 3 minutes after the before the top of the hour, and I want to take the opportunity to summarize today's session. And we have spotlighted a single powerful idea that large language models can act as intelligent agents, and this could range from pinpointing promising drug targets to zero-shot parsing of clinical notes, to steering molecular structures towards optimal properties. And these LLM-driven agents show that how language itself can orchestrate discovery, reasoning, and design at speeds that is unthinkable a few years ago. And as we close this year's Healthcare AI Forum, we are grateful for the Northwestern and Greater Chicago area research community and your continuous support, and also to our colleagues and friends who have joined us from Stony Brook, Wisconsin Medicine, UCLA, and Emory and Ohio State today. And you helped weave your diverse perspectives into our shared fabric of innovation. And these insights spanning governance, multimodal pipelines, patient-centric AI, large language models, remind us that the collaboration is our greatest catalyst. So let's carry this momentum forward. Over the summer, we'll be curating next year's lineup, and you can expect deeper dives into trustworthy generative AI, federated learning at scale, and patient-centric design. Until then, keep questioning, keep building, and keep imagining the healthier world we can create when clinical insights meets computational ingenuity. See you all in the fall. Thank you, everyone. Take care.
Bye.
Thank you.